So continuity is has three very specific parts that we're going to need to check for. It's kind of like one of those sections where it just is this section and then we just sort of say, oh, well, if the function is continuous, and then we kind of wave our hands at it. So we never really check for continuity, but we have to know how to look for it in case we do. So first of all, the definition. So continuity at a point. So we're going to assume that f of x is defined on an open interval, so that means just a chunk of x's, containing the value x equals a. So we have some sort of chunk of, x-axis where the value a is contained. So f is continuous at x equals a if the limit as x approaches a of f of x equals f of a. If the limit does not exist or does not equal f of a, then what we say is f of x has a discontinuity at x equals a. Okay, so all of that, here we go. For a function f to be continuous at a point x equals a, three things must be true, and they are this. So first of all, f of a is defined, so you don't have a hole or an asymptote. The limit as x approaches a of f of x exists, so the left side and the right side are the same, right, holes filled in. And the limit as x approaches a of f of x equals f of a. So just so you know, right, most of the things that we have are continuous functions. So polynomials, definitely continuous. Rational functions, so right, fraction of polynomials, they're continuous on the domain. Okay, so not where, right, at their vertical asymptote, but that x value is not in the domain, so we're okay there. Trig functions on their domains. So for sine and cosine, that's all real numbers, but tangent and secant and those, they have their asymptotes, so we'd have to restrict it to just the values in the domain. And then exponential and log functions, again, log functions on their domain. So I don't know if you guys can hear that, but all of the animals are wanting to be part of the lesson today. So we'll kind of look at, you'll get a chance to decide, right, in your homework at least, if a function is not continuous, what reason, which one of these three things it's missing. So sometimes it'll just be a hole that's not filled in. Sometimes the limit won't exist, right, for one reason or another. And usually the limit doesn't exist. This is if the left side and right side, right, don't match. Left side and right side must match. And then the limit does not equal the function value. This is where you might have a hole and then it gets filled in someplace else. Now we can have left and right-sided continuity, so we can be left continuous. And what that's going to look like is that the limit as x goes to a from the left is where, right, your function gets evaluated. So this just means, right, from the left, the dot is filled in. Right, so if you have a hole and you're coming from the left and it's filled in on that side, then you would say, oh, it's left continuous. Right continuous, right, if you come in from the right, right? So from the right has the filled in dot. And you're going to see a couple of examples down here. I guess just one. Okay, so here we go. So there are three types of discontinuities that we'll talk about. So the first one is a removable discontinuity, and I couldn't make this open circle bigger, but there's an open circle down here at 1, -3. So that's an open circle, and then it got filled in up here at the point 1, 1. Okay, so this is called a removable discontinuity. So a function is said to have a removable discontinuity at x equals a, so in this particular example, right, at x equals 1, if f is either not defined or not continuous at x equals a. Okay? And f of a could be defined or redefined so that f of x is continuous at x equals a. Okay? So in this case, x equals 1 is a removable, oh, there's no e there, is there? Removable discontinuity. So let's look at our definitions again, right? F of a is defined. That's true, right? For this function, f of 1 is defined. So that's okay. Part 2, the limit of f of x as x approaches 1 exists. Yep, the limit does exist. So the limit down here, right, as x approaches 1 of f of x is negative 3, right? So the limit of the function is negative 3. So the continuity part that we fail on this removable is that third one, that the limit is not the same as the function value, right? The function value is 1, 1. The limit is 1, negative 3. Okay? So that's a removable discontinuity. So we could fix it if we wanted to, quote unquote, fix it by redefining f at x equals 1. Okay, jump discontinuity. So that's our next type. And that has, right, a jump between the two. So if you notice this, right, it looks like I've got a parabola on the left, I've got a line on the right, and there's a jump. Notice this is the open circle down here from the left. So for this middle graph, we would say, which one? Is this left or right continuous? This one is right continuous because it's from the right where we get to the filled in circle. Okay. So a function is said to have a jump discontinuity at x equals a. So in this case, right, a is being played by 0. If the limit as x approaches a from the left exists, and the limit as x approaches a from the right exists, but the two limits aren't equal to each other. Okay. And the jump does not have to be this big, right? I could have, right, the parabola could have come in here at y equals positive 3 as well, and that's still, right, a jump discontinuity. Make sure they're not both filled in as well, because then, right, you violated the function rule. Each x gets only one y. Okay, so jump discontinuity, not much to fix about that, right? It just is. And then the final type of discontinuity is an infinite discontinuity, and that's just going to be these vertical asymptotes. Now, it can either be, right, one goes to negative infinity and one side goes to positive infinity, or they could both go to positive infinity or negative infinity. Okay? So a function is said to have an infinite discontinuity if either or both is true. So the limit as x approaches a from the right of f is either plus or minus infinity, and then the same thing as you approach a from the left, plus or minus infinity. Okay, so those are like the formal definitions, formal vocabulary for continuity. But really, it's can you draw the graph without lifting up your pencil? If you can say yes, then you have a continuous function. So I know one of the things that you do get asked in your homework is to redefine a function so that it is continuous. So here's an example. So f of x equals 2x minus 5 times x minus 3 divided by x minus 3. Now, unfortunately, I didn't bring my calculator down with me. If you have yours, what I would like you to do is go ahead and graph this function in y1, and you don't have to multiply it out. You can just do those parentheses with your division. You will need parentheses around the denominator as well. When you type that into y1, what you're going to see, here, I've got another piece of paper, hold on. What you're going to see is a diagonal line. Slope of 2, y-intercept of negative 5. Why is that? Exactly, right? Because, right, the x minus 3s are going to cancel. we just get 2x minus 5. So really, y equals 2x minus 5 is equivalent to this much bigger version of f of x everywhere except, so the way we write that is for all. So since I've been typing, I don't use this symbol because it's harder for me to find on the computer, but upside down capital A, for all, if you're writing and trying to keep up, for all x not equal to 3. Right? So this linear function and your f of x rational function have exactly the same outputs for every single x value except for 1. Okay? So that means, right, that value, that x equals 3, is a removable discontinuity. So here's what I want you to do. So if you have the rational function, right, typed into your graphing calculator, go ahead and try to find the value at x equals 3. And you'll see, right, if you do the value where x equals 3, that y spot is going to be completely blank, right? It's not defined there. You've got a hole in your graph. So if I come over here to 3, I'm going to have a hole in my graph if I've graphed the rational. Okay. So what we need to do is we just need to fill in that hole. And to find the y value that's going to fill in that hole, I'm just going to take this 3 and plug it into the linear function. So if x equals 3, my line goes through the point, what is that, 6, 5. So if I redefine my f of x, so f of x equals 2x minus 5 times x minus 3 over x minus 3 for all x not equal to 3, and it equals 1 for x equals 3. Okay? So what you do is you find the equivalent function that's defined where x equals 3, plug 3 in, come up with the y value that'll fill in the dot.